Dear students, welcome to this online class on applications of NMR spectroscopy. Number one, NMR spectroscopy is the most powerful tool for structural elucidation to determine the structure of an unknown molecule, especially organic compounds. In elucidating structure, we deduce four important informations from the NMR spectrum of a molecule. That is, one is we look at the number of NMR signals in the spectrum which tell you about the number of different types of protons present in the compound. That means different chemically non-equivalent protons in the compound. Secondly, the information we get from NMR spectrum is the peak area. The peak area, the area of the signal or the peak height, it is a measure of the number of protons of each type which gives that signal. Third point is the chemical shift value of each signal indicate what? The nature of the proton or the chemical environment of the proton, how far it is shielded or deshielded. And finally, we can deduce another important information from the multiplicity of each signal. In the previous class, we have learned about spin-spin coupling, which lead to splitting of NMR signal. So the multiplicity of a signal, whether it is a doublet or a singlet or a triplet, it tell you what? It gives the information about the neighboring protons, isn't it? Because a signal is split by a given set of neighboring protons. If there are n nearby protons, that will split the signal into n plus 1 number of lines. So the multiplicity of a signal is telling you about how many neighboring protons are there. So these four informations can be deduced from an NMR spectrum, which help you to deduce the structure of an organic molecule. Apart from that, other applications are, we can study about hydrogen bonding, whether there is hydrogen bonding present or the extent of hydrogen bonding is reflected in the chemical shift value, because due to hydrogen bonding there will be a little bit of deshielding. Okay, because of the hydrogen bonding, the electron density will be reduced around the proton, and that leads to deshielding, or the frequency will increase due to hydrogen bonding. So looking at the chemical shift value, we can predict the presence and the extent of hydrogen bonding in a molecule like alcohol, amines, etc. Then third application is, we can study about tautomerism, because in tautomerism, like for example keto-enol tautomerism, there is hydrogen transfer. So we can compare the NMR spectrum of the two forms, keto form and enol form, and study about this tautomerism. The next application, we can use NMR for kinetic studies, we can use NMR for quantitative analysis, and finally the most important application of NMR in medical field or medical diagnosis is MRI scan. The most powerful diagnostic tool nowadays used for scanning purpose, that is MRI, magnetic resonance imaging, which is based on NMR, proton NMR. In MRI, we are able to take the photograph of internal organs. What's the principle? We know that our body contains a good amount of water, which is present in different concentration in different organs, and water contains hydrogen. So we can get the image of various organs based on the concentration of water present in various organs. and this is superior to X-ray, which can photograph only the bonds, and it is more harmful also. Comparatively, radio waves used in NMR or MRI is less energetic and it is less harmful. Now we go to the detailed application of structural elucidation, or we will see how NMR is obtained for these molecules according to our syllabus. Let's take one by one. If you are given a molecule and asked to interpret the NMR spectrum, how you do it? Let's take one by one. Starting with acetone. What you do first is write the structure. So acetone is CH3, CO, CH3. Then secondly, you detect the number of and type of protons. If this is A, it's very clear this is also A. Acetone contains only one type of NMR, one type of proton. So what about the NMR spectrum? We can see it will be like this. As usual, we del equal 0, that is TMS. See, there are 6 equivalent protons connected to CO. You know the chemical shift value is somewhere around 2 to 2.5. So we get a peak, a little large peak, a singlet. There's no cup splitting, of course. You can show TMS, or if you don't show, doesn't matter. This is TMS, for example, del equals 0, and this is the methyl proton. Okay, 2 methyl proton. So the peak height corresponds to 6 proton. There is no splitting here, and the chemical shift value is around somewhere around 2 or 2 to 2.5, like that. Okay. Let's now take ethanol, the second molecule. In the case of ethanol, see, it's very interesting. See, ethanol is the most studied molecule in NMR. Historically, the first molecule which was studied in NMR was ethanol. Let us draw the structure: CH3, CH2OH. Now actually there are 2 types of NMR spectroscopy. That is, one is low resolution NMR and the other is high resolution NMR. So what is low resolution NMR? That is NMR spectroscopy using a very weak field and run at a low frequency, where you will not see the spin-spin coupling. That is not seen. That is low resolution. Whereas high resolution will include the spin-spin coupling, and splitting of signals will be seen. So in the low resolution NMR of ethanol, let us first classify the protons. If this is A, this is B, this is C. There are 3 different types of protons in ethanol. So you will be getting 3 NMR peaks. Okay, and let's see how it comes. Which will be most de-shielded? OH, of course, comes around 4 to 5, and there's a very small peak because only one proton is there, one hydrogen. Then comes CH2, because connected to oxygen, comes around 3 to 4 somewhere, and it will be a little larger. And then comes methyl proton, which will be somewhere around 1 to 1.5, like that, and that will be the tallest. You understand? So we can mark it. This is the OH peak, this is the CH2 peak, this is CH3 peak. Okay, right? You can see the ratio 1:2:3 ratio, the peak height. As I said, the peak height indicates the number of protons of each type. Now, this is low resolution. In high resolution NMR, ethanol will show a more interesting spectrum, because there will be spin-spin coupling seen in the spectrum. Okay, we have learned in the previous class spin-spin coupling. Let us predict the multiplicity. Okay, this CH3 signal will be split by CH2 proton into how many? 2 plus 1 equal 3. So you get a triplet. This will be split into a triplet. Now let's consider this one. Okay, here in high resolution we discuss two types of NMR for ethanol. One is extra pure, 100% ethanol for example. If it is extra pure, you get the NMR spectrum in full swing. Another is impure ethanol, or let's say acidified ethanol. Ethanol containing some acid. In that case, acidified ethanol. Okay. There will be slight difference between the spectrum of the two. In extra pure, we get complete splitting. So as I said, this will be a triplet. Now, this OH proton signal is split by CH2 into how many? In the same way, 2 protons are there, so 2 plus 1 equal 3, another triplet. Triplet for 1 proton. Finally, CH2 split by both sides. You can see 3 proton here, 1 proton here. So how many? 3 plus 1 into 1 plus 1 equal how many? 8. It will be an octet. So let us show the spectrum now. This will be into a triplet, okay? In the ratio 1:2, 2:1, like this. Now this will be an octet. So it's very difficult to show that octet because only 2 protons into signal into octet means it will be a very complicated, complex multiplet. It will come like this. Okay, right. Okay. Not exactly octet, somewhere like that, something like that. And finally, CH3 signal will be split into a triplet. There will be a clear triplet. One in the ratio, in the intensity ratio, 1:2, 2:1. Right? This is a kind of NMR spectrum obtained for extra pure or 100% ethanol. Now, when ethanol is slightly acidified, there will be a little difference, some difference in the NMR spectrum. What is the difference? It's very interesting. Okay, see, when it is acidified, what happens, this OH proton undergo migration, continuous transfer from one molecule to the other with the help of acid. Okay, so this OH proton will not involve in spin-spin coupling for CH2, correct? That means CH2 signal is not split by OH proton, it is split only by CH3. Okay, so no difference for CH3 signal. That will be split by CH2 into, as before, 2 plus 1 equal 3 into a triplet, that is fine. Now CH2 signal is split only by this CH3. So it will be 3 plus 1 equal 4, that is a quartet. So OH signal is not split by CH2. The CH2 signal is not split by OH, and also OH signal is not split by CH2. Why? Because OH proton is not stable there. It is continuously migrating. That is called solvent exchange phenomena. We can show it like this. See? C2H5OH, okay, this is ethanol. You know that oxygen contains 2 lone pairs. In presence of acid, that is H plus, that get protonated. Suppose, let me mark this hydrogen as HA and this is HB, that is present in the acid. What happens? This gets protonated and it becomes C2H5OH. Okay. Using the lone pair, it gets protonated, and this is A and this is B. And of course, there will be a positive charge here on oxygen. What happens? Now this can undergo deprotonation. In that process, this proton may get lost. So there is exchange of proton. So this proton is not stable on any molecule. It keeps continuously getting exchanged with other molecules. So this proton cannot feel different spin alignment of this neighboring proton, so no coupling. And also this CH2 proton also cannot feel different spin alignment of this OH proton because it is not stable there. So the NMR signal, NMR spectrum will be now like this. This will be a triplet, no change. This is now a quartet instead of an octet because it is split only by CH3. So a quartet is in which intensity ratio? 1:3:3:1, isn't it? So 1:3:3:1 ratio. Okay, and what about OH signal? OH signal will be there because that proton is there somewhere. So this will give, it will appear as a singlet without any coupling. So OH signal will now appear as a singlet, right? Now regarding the chemical shift value, OH will be somewhere around 4 to 5, somewhere around 4 to 5, nearly 5. CH2 connected oxygen will be, from the chemical shift value somewhere around 4, 3.5 to 4, and CH3 will be somewhere around 1.2. This is the chemical shift value. So as I said earlier, NMR spectrum tell you 4 things. One, number of signals. There are 3 signals. That means ethanol contain 3 different types of proton. Number 2, the peak height means we can integrate these peaks, and the integration height or peak height tell you the number of protons of each type. Okay, and thirdly, the chemical shift value tell you about the chemical environment of each proton, how far it is shielded or deshielded. And finally, the multiplicity. For example, this CH3 signal split into triplet tell you what? That CH2 is connected to CH2, CH3 is connected to CH2. That's why it is split into a triplet. These are the 4 informations. Okay. Now there is one point regarding spin-spin coupling, a concept, that is, see, in a multiplet there is a separation between the 2 peaks. See, if I show it separately, suppose this is a triplet. Okay. Now this separation, this gap is called coupling constant. You should note that. What is called a coupling constant, represented by the letter J. So what is coupling constant? The separation between the peaks in a multiplet. Now it is expressed in Hertz. It is a measure of effectiveness of coupling. Effectiveness of coupling interaction. More the coupling interaction, more will be the coupling constant or the separation. And it's a reciprocal phenomena. That means when CH2 and CH3 are coupling each other, the coupling constant J here will be same as that in this one. Both will be same for 2 coupling partners. And it is independent of the applied field strength as well as the frequency used for this NMR instrument. Okay, so that's about ethanol. So ethanol is a very important molecule in NMR spectroscopy. Now let us go to the remaining molecules quickly. Now it's very easy for you to explain. The next molecule is, I didn't ask you to predict the spectrum. You can work it out. Okay. What's the next molecule? 1,1-Tripromo Ethane. What's the structure? Ethane, 2 carbon. 1,1,2. So there are 2 bromine here and 1 bromine here. Ethane. So this is CHBr2, CH2Br, isn't it? What about the number of NMR signals? Here there is 1 proton with 1 chemical environment A, and this is B, right? So you will have 2 NMR signals. And how it will appear? See, you will have 2 signals. This A connected to 2 bromine will be more deshielded. So A will be coming to the side, somewhere around, it will come around 4. See, when there is 1 bromine, it will be somewhere around 2. When 2 bromines, it will be somewhere around 4. So you will have 1 signal here. And what about splitting? That's very important. What about splitting? This is split by this proton, so you have to predict the multiplicity. So 2 plus 1 equal 3, so there will be a triplet for this one. What about this one? These two proton will, the signal of this CH2 will be split by this one. 1 plus 1 equal 2, that's a doublet. So we can go like this. This signal is a triplet for one proton, so the peak height will be less. Triplet is 1:2:1 ratio, somewhere around 4. Okay, then this connected to one bromine somewhere around 2 proton, and that is a doublet. So it is somewhere here, 2 proton doublet with more peak area. Doublet means 1:1 ratio, right? Like this. So this is the signal of CH and this is the signal of CH2, right? That's how we predict. Now we go to the next molecule. What next? Next molecule is acetaldehyde. Draw the structure. Acetaldehyde, CH3, CHO, acetaldehyde or ethanol. How many signals? This is A and this is connected to this neighboring carbon, so this is B. 2 signal. Now what about splitting? This signal is split by 1 proton here, so 1 plus 1 equal 2. It's a doublet. This signal is split by 3 proton, so 3 plus 1 equal 4 into a quartet. Let us draw. See, aldehyde proton due to anisotropic effect appear at where? 9 to 11, right? It's very deshielded and it is a quartet. Okay, 1 proton quartet means it's a very small signal. Somewhere here. Quartet means 1:3:3:1. Okay, very small. And this CH3 proton as a doublet, it is connected to CO, so comes around 2 to 2.5. Somewhere here, it will be a doublet, a very large doublet, because there are 3 protons. So this is coming around somewhere 9 or 10 like that, and this is at 2 to 2.5. You need to predict rough value only here, but you should know this is the CHO proton and this is the CH3 proton. Correct? Okay. Next one is propanoic acid. Okay. Propanoic acid is CH3, okay. Propanoic acid is left to you. You should do it as a homework. Let me do this toluene. Toluene, is aromatic compound, right? CH3. There are aromatic protons. 5 aromatic protons are there. What about the NMR spectrum here? How many signals? Aromatic protons are, deshielded due to anisotropic effect. This is B. All are B. So you will get 2 signals, right? And there will be no coupling here because it's not neighboring carbon. See, this is one carbon and this carbon doesn't have proton. It is on this carbon. So no coupling between these two. So you will get 2 singlets actually. Okay. So this is most deshielded aromatic proton 6 to 9. Okay. It comes appear between 6 to 9. You get a very large signal for this aromatic proton. Okay, benzene protons, and CH3 benzylic position 2 to 2.5 comes and you get another signal for 3 protons. So there are 5 protons are there here, and here it is CH3, that is 3 protons. So you can see the high difference. Okay, but when it is benzoic acid, see, these two are not. If you look, you may feel this is in different chemical, of course this different chemical environment, and these aromatic protons are giving only a singlet. But when it is carboxylic acid, see, when it is COH, this group is highly deactivating, minus R effect, and that will make the aromatic proton all non-equivalent actually. That means if this is A, this is also A, ortho protons, then this is meta, this is B, and this is para. There are 3 different aromatic protons and they can couple also each other. Okay, because this group is making all these positions non-equivalent. when it was methyl group, it's a carbon and there is not much difference in electronegativity, or the aromatic protons are almost equivalent. Here it is quite different. So this will be coupling also, and this aromatic signal in this case will appear as a complex multiplet, something like this. Okay, it appears as a multiplet. If you use a very powerful and very much resolving spectrometer, this will be seen, this will have a very clear pattern, and how these ortho coupling, meta coupling and para coupling takes place, and what is the coupling constant, it's all well defined, and that is beyond the scope of our discussion now. So that is how we get the NMR spectrum. We will discuss these molecules in more detail in the coming discussions, and this is the end of this NMR spectroscopy and the module as a whole. See you in the next class. Thank you.